Not so long ago, in the grand timeline of human history, we believed something that now seems almost laughable. Earth was the center of the universe. Everything revolved around us. That was the consensus. Everyone accepted this as absolute truth, and anyone who dared to challenge it, they were branded as godless rebels, punished, sometimes even killed. Think about that. Something we now consider basic common knowledge, something we laugh at anyone for denying, once cost people their freedom, even their lives. It was Copernicus who started the revolution, even though he still got some things wrong, like placing the sun at the center of the universe. His idea was nothing short of revolutionary for his time. In the 15th century, when most people believed the Earth was flat and sat at the heart of everything, Copernicus dared to see it differently. And yet here we are in 2026, and there are still people who insist the Earth is flat. Those folks would have been perfectly happy back in the 15th century. But anyway, of course, this shift in thinking didn't happen overnight. Copernicus actually had the fortune, if you can call it that, of dying of natural causes within a year of publishing his work. He escaped the wrath of the conservative establishment. But the establishment continued to reject his ideas for centuries. Then, in the 17th and 18th centuries, scientists like Newton finally cemented this new understanding. We learned that we live on a planet orbiting an average star. Nothing special, just one world among many. By the early 20th century, we made another humbling discovery. There were other galaxies out there. The universe wasn't centered on anything. It was isotropic, the same in every direction. And with that, our ancient quest to be special finally ended. We turned our attention to far bigger questions. Then came 1998, and everything changed again. A study using Type 1a supernovae. These are exploding stars that shine with a known predictable brightness, revealed something nobody expected. The universe wasn't just expanding, its expansion was accelerating. We already knew the universe was expanding, and if space were truly empty, you'd expect that expansion to be steady, maybe even slowing down over time. But something was pushing it faster. Something was accelerating the expansion of the entire universe. Something we couldn't see, or things, or whatever it was. But before we can answer that, there's a question we need to ask first. Where did matter come from? Where do we come from? And not just us. Everything on our planet, every star, every galaxy. Look at this iconic photograph taken by the Hubble Space Telescope. Tens of thousands of galaxies leap out at you. Some of them are incredibly faint because they're incredibly old. Because that light has been traveling for almost 13 billion years. When we look through this telescope, we're not just looking at distant space. We're looking back in time, all the way to the beginning, to the Big Bang. But here's the real question. Where did the matter that makes up everything, including all those galaxies, actually come from? Stardust. Where did it come from? And it turns out we might actually have an answer to this cosmic mystery. We believe that everything we can see emerged from a titanic battle between two things we can't see: dark matter and dark energy, something we only recently discovered. Together, dark matter and dark energy rule the universe. But to understand this, we needed to look back even further than Hubble could see. We needed to travel back to the very beginning. In 2001, we launched a satellite called WMAP into space. Its mission? to capture the first light of the universe. The first light of the universe? Yes, we're talking about the light that formed roughly 380,000 years after the Big Bang, the moment when the universe cooled enough for light to finally travel freely through space. This is the phenomenon that helped give birth to the Big Bang theory itself, the cosmic microwave background radiation. It was discovered completely by accident. In the 1960s, two astronomers, Arno Penzias and Robert Wilson, kept picking up a strange, persistent hiss in their radio antenna. No matter where they pointed it, the noise was everywhere. That noise turned out to be a legacy of the Big Bang itself. In 1992, NASA's COBE satellite provided the first definitive proof that this radiation existed. Then WMAP set out to create a detailed map of it. After 9 years of painstaking observations, this extraordinary image emerged. This is what scientists call the baby photo of the universe. What you're looking at is the signature of the universe's birth, the fingerprint of the Big Bang. By reading these color patterns, astronomers can trace the entire history of the universe from its birth. They can calculate its age with remarkable precision. 13.7 billion years. The most important thing this data revealed was this. More than 95% of the universe is filled with what we call dark matter and dark energy, a force and a substance that push the very limits of human comprehension.
So, how did we reach this conclusion? Let's talk about that.
First, we need to talk about speed. Our Earth orbits the Sun at 1,670 kilometers per hour. That's already fast. But do you know how fast our entire solar system orbits the center of the Milky Way? About 800,000 kilometers per hour. That's an absolutely staggering speed. But here's where things get strange. In our solar system, the further a planet is from the Sun, the slower it orbits. That's Newton's laws at work. The further from the center, the less gravitational pull, the slower the speed. Simple. So naturally, you'd expect the same thing to happen in galaxies. Stars further from the galactic center should orbit slower than stars closer to it. That's what the math predicts. But here's the thing. No matter where they are in the galaxy, whether near the center or at the very edge, the stars all orbit at nearly the same speed. Some of the outer stars even move faster than expected. Wait, what? That made absolutely no sense. And the woman who made this discovery had a story just as extraordinary as the finding itself. Vera Rubin. In the 1960s and 70s, astronomy was dominated by men, but Rubin, who had been fascinated by the stars since childhood, chose to look where nobody else was looking. While everyone focused on galaxy centers, she studied the stars at the outer edges, and that's where she found something that would change everything. This was truly extraordinary, and it demanded an explanation. Vera Rubin, a name far too few people know, was the one who would provide it. She did it despite being rejected from Princeton's astronomy program because she was a woman, despite raising 4 children while pursuing her research. She did it anyway. According to Rubin, there could only be one explanation. Take the Andromeda Galaxy, for example, one of the closest spiral galaxies to us. The stars beyond the visible edge of the galaxy were moving as if they were close to the center, as if something invisible was holding them, pulling them. The only explanation? Even where there was no light, something had to be there, some kind of matter. It had to be dark matter. Rubin's observations showed us that galaxies are embedded inside a halo made of this dark matter, a substance our telescopes simply cannot detect.
Galaxies don't float in empty space. They move through this invisible substance. That most of a galaxy's mass comes from this invisible matter. When we look up at the night sky, we're only seeing a tiny fraction of what's actually there. We're looking at specks of dust in an ocean filled with invisible matter. We're swimming in an ocean we can't even see. But here's the real problem, the biggest problem. Dark matter doesn't resemble any matter we know. Nothing we are, nothing we've seen, no planet, no star, no galaxy contains any trace of this stuff. It's unlike anything in our experience. And that's why searching for dark matter feels like stumbling through true darkness.
But make no mistake, we are certain it exists. And one of the strongest pieces of evidence comes from something fundamental: how stars form in the first place.
Think about it. In the beginning, there was nothing pulling atoms together, no reason for them to gather. So how did stars form? What made atoms decide to come together and build stars? And here's the answer. When we look at the WMAP data, we can see regions where dark matter was denser than average. That density created gravitational pull, and it was at those exact points that atoms were drawn together and stars were born.
They're out there, somewhere. We just don't know where exactly. But are we trying to find out? Absolutely. Where are we looking? Right here, at CERN, inside the Large Hadron Collider.
So what exactly are we doing at CERN?
Here's the thing. We've touched on the Standard Model and the 4 fundamental forces of the universe in a previous video, and we'll dive deeper in future ones. But when we talk about the Standard Model, we're talking about subatomic particles, the fundamental building blocks that we believe make up atoms, and therefore everything visible in the universe.
There are 2 families: fermions, the particles that make up all the matter we can see, and bosons, the particles that carry forces between fermions. Think of fermions as the bricks and bosons as the mortar holding them together.
3 fundamental forces: the strong nuclear force, the weak nuclear force, and electromagnetism are all carried by these bosons. And if you're wondering about gravity, the Standard Model still hasn't been able to include it in the equation, but someday it will. Anyway, among these fermions and bosons, we find quarks, the most fundamental particles that make up the protons and neutrons inside every atom. They're the smallest particles we know of that have mass. But here's the question: where does that mass come from? The answer comes from Peter Higgs. These particles move through something called the Higgs field, an invisible field that is believed to fill the entire universe. You're in it right now. Everything is. It's everywhere.
As particles move through this field, they're slowed down, and that slowing is what gives them mass. Without the Higgs field, everything would travel at the speed of light. Everything would be pure energy. Nothing, absolutely nothing, would exist as matter.
Peter Higgs predicted this field back in the 1960s, but it took nearly 50 years to prove it. In 2012, the particle collider at CERN finally discovered the Higgs boson and confirmed the field was real.
In 2013, Peter Higgs was awarded the Nobel Prize in Physics for this discovery.
The Higgs boson itself is a particle that emerges from waves in the Higgs field. Think of it like this: the Higgs field is a calm ocean. To detect it, you need to create a splash, a wave. And the way you create that splash is by smashing particles together at incredible energies. This Higgs boson, together with the Higgs field, is the particle that gives mass to all known particles, and therefore to us. That's why it earned the nickname the God particle. Physicists don't love that name, by the way, but you have to admit it sticks. So why does the Higgs boson matter beyond mass? Because some scientists believe it could be a portal, a doorway to understanding dark matter. We haven't gotten there yet, but the search is very much alive.
And when we finally crack dark matter, we'll be able to explain how galaxies form, how galaxy clusters form, how everything in the universe came to be.
But dark matter has an enemy, something even darker.
The other force in the battle I mentioned at the beginning. As astronomers studied distant galaxies and the remnants of the Big Bang, they discovered something unexpected. For the first 8 billion years after the Big Bang, the universe expanded, but it was slowing down, just as everyone predicted. In fact, many believed this deceleration would continue, that the expansion would eventually stop entirely and then reverse in what scientists called the Big Crunch.
But then, 8 billion years in, something happened. Something very strange. The expansion of the universe didn't just stop slowing down. It started speeding up, faster and faster.
And as far as we know, this acceleration is only getting stronger. Today, the expansion rate is estimated at roughly 240,000 kilometers per hour, and it's still increasing. Our data suggests this will continue forever.
So what happened? What could possibly cause something this extraordinary?
We don't know. And that's exactly why we call it dark energy.
An extraordinary force that makes up 68% of the entire universe. We're certain it's there. We just can't explain it yet.
But let's save that story for the next video. We'll continue this series with a deep dive into dark energy. And after that, some truly exciting topics are waiting for us. If you want to keep exploring the universe with us, make sure to subscribe and hit that notification bell. Your support helps Science Mosaic keep growing, just like the universe itself. Follow us on social media, join the conversation, and share the science. As always, until next time, we're glad you're here.